The content of this video will be about the existence of limit. So take note that when we are studying about limit, we are not studying about the function itself, but its behavior towards a certain point or where it is approaching to. The limit of a function can be mathematically described as the limit of f of x as x approaches a is equal to L. Take note that f of x is any function and a is any number where we would want to study the value of our x. And when our x are the different values that would approach a certain value, x is equal to a. Take note that x should be near our a. Example 5 at x is equal to 5. Our x could be equal to 5.01, 5.02, 4.99, 4.98. And then of course, the value of our L. Take note that the L is the value of the function when we are substituting the different value of x near to our a. So if we can directly substitute the value at x is equal to a in our function, therefore we may say that that function is defined. For the graphical representation of our equation limit of f of x is equal to L, so I will draw a Cartesian plane. So we have our x and y coordinates. So take note that we will draw our function f of x. So this function will represent an equation f of x. And then let's say we'll have a value of a, wherein this a is equal to x, and upon substituting the value of a, we'll have a corresponding value of y, which is our L, at a certain point. So therefore, as we go on into the points, so we can see that the points near the point x of f of x, wherein your x is equal to a and your f of x is equal to L, has a behavior near to our a. As you can see, at a specified function f of x, there's a corresponding value of y as we will substitute the value of x. So we may say that the function is defined if we would substitute the value of a directly to f of x, and we can have a direct answer or a direct solution of the limit. But in the second case, wherein if you would substitute the value of a directly to the function, we will have a value that is undefined or indeterminate. So therefore, the best thing to do there is to substitute a value that is near to the point a, wherein x is approximately equal to a but not equal to a. So if you would use that definition of limit, therefore we can get a value that is approximately equal to that value of the limit. But in case you can see that the points are not converging, instead they are diverging and diverging and diverging until they will reach a very high or very big number. So therefore we conclude that that type of limit may be an infinity. The limit of a function, therefore, as it approaches x is equal to a, is not necessarily equal to the value of a. Thus, the limit of f of x as x approaches a can assume a value different from f of a. The existence of a limit can be the limit of a function as x approaches a exists if f of a is defined or f approaches the same value as a moves closer to x from both directions. Ibig sabihin nun, magko-converge sila. Hindi magda-diverge. Pag nag-diverge yun, so therefore, your conclusion may be undefined or infinite.
So in order to illustrate further the existence of limit, let's have this example. Limit of x squared plus 3x plus 4 as x approaches 2. So in the first proposition, according to the existence of the limit, f of c is defined. So the limit of a function as x approaches a exists if f of a is defined. So if f of a is defined, so by basically substituting the value of our limit, which is your a, to the values of a, to the values of x, we will get the limit of this equation. So getting the limit of this one, so we will have the limit of x squared plus 3x plus 4 as x approaches 2 is equal to the value of 2 squared plus 3 multiplied by 2 plus 4, which is equal to 4 plus 6 plus 4, or it is equal to 14.
So in order to demonstrate the graphical solution of the function x squared plus 3x plus 4, I use the application GeoGebra. So upon inputting the value of the variables or the equation, so you can see a graph, and the second graph is x is equal to 2, wherein that is the value of the limit at x equals a, wherein our a is 2 and it intersects at 214, meaning that the function is defined because there is an intersection between the value of a and the function when you will substitute the value of a. So after determining that the function is defined through graphical solution, I use the table of values wherein I started at the value of 1.95 and ended at the value of 2.05. So in order for you to see the difference, the small difference, my step is that it would increment at 0.01. So you can see the value of limit that is behaving upon a point A. Okay? So halos magkakalapit lang sila. And upon that, you can see that at a certain value near to the limit, which is x is equal to a, there is a corresponding value which is near to him, which is if you will round it up or round it down, you have 14. If you will use the lower values, wherein we have the value from the increment of 1.95, you can see that it is near to 14 if you would round it up. And if you would choose the second value, or in the values that are greater than 14 but near to greater than 2 but near to 2, like your 2.01, you can see that if you would round it down, it is always equal to 14. So this proves the value of our limit that was solved from our calculation, which is the limit of the function as x approaches 2 is always equal to 14.
So for the proof of the second proposition, let us solve this example. The limit of x squared minus 9 divided by x minus 3 as x approaches 3. So as you can see, if you would substitute directly the value of 3, the function is not defined because x squared minus 9 divided by 0 is just equal to undefined, right? So therefore, in order to solve for the value of this function, let us manipulate the formula or the equation, which is equal to x squared minus 9 divided by x minus 3. So therefore, by further manipulation of this one, we'll have a value equal to the limit of x minus 3 multiplied by x plus 3 divided by x minus 3. So you can see that the value of x minus 3 divided by x minus 3 is equal to 1, right? So therefore, we'll have a value of x plus 3 and the limit of x approaches 3. The limit of x approaches 3. So later on, you will see that the graph of x of this function is just linear. Okay, so therefore we may ready to evaluate your limit of x plus 3 as x approaches 3. So therefore we'll have a value equal to 3 plus 3 is equal to 6. Example, I will show the second proposition of limits, or the second proposition on the existence of a limit, wherein the limit of a function as x approaches a exists if f approaches the same value as x, moves closer to a from both directions. So in this example, I have my equation equal to x squared minus 9 divided by x minus 3 as the limit of x approaches 3. So therefore, if we would directly substitute the value of 3 in this one, we will have a value equal to undefined. Okay, so therefore we would need to have values that is near to 3. Probably by graphing this function, we'll have a value equal to, we will have a graph which is this one. Okay, so this will be our graph. This is a linear graph, because basically we can manipulate this equation into a linear graph. We'll have an x plus 3 equation. Okay, so in order to demonstrate that the value of x is equal to 3 is undefined here, so I would put a value of x is equal to 3. You will see later on that Even in the graph, you can see that they're intersecting, but particularly there is no intersection between our x is equal to 3 and the function f of x is equal to x squared minus 9 divided by x minus 3. Because basically, if you would substitute the value of 3, we'll have an undefined answer. Okay? So therefore, the concept of limits is to describe how a function behaves near a point. So instead of that point that we are talking about is your x is equal to 3. So in order to get the limit of it at x is equal to 3, so therefore let us modify the equation into its special product form and then cancel the same terms. But using a graphical method, we would substitute values that is near to the value equal to 3. Okay, so what are these values? So probably we can use this table of values. So I would start in the value equal to 2.98. 2.97 or 2.98, and the next is to 3.01 or 3. Let's say 3.02. Okay, and then I would put the step at 0.001. So in order to demonstrate further that the value of the limit of x squared minus 9 divided by x minus 3 as x approaches 3 is 6. So you can see that we'll have a values from 2.98 which is near to 6. Okay? So, so if you would round up this one, it is equal to 6. Okay? But particularly at a value equal to 3, it is undefined. So that's why it has a question mark. So therefore wala siyang, if you would get the value at the function of y, so therefore there is what you call a hole. Okay? So at that point, that corresponds to x is equal to 3. For x sufficiently close to 3, represented by the two arrowheads on the x-axis, the two arrowheads on the y-axis representing function values of f of x simultaneously get closer and closer to the number 6. We say 6 is the limit of f of x as x approaches 3. Okay? So let's say, tingnan natin yung show points. Okay, these are the points. Okay, so you can see that the points are going to the value equal to 6. Okay, so this is our value 6 and the points are near our value 6. And take note that at the value 6, we have our void point or yung the point where our x is equal to 3 is put in. So ito yun. So you can see that there is a void in that point. Okay.
In order to solve and manipulate the problems involving limit equations, let us first know the different theorems involving our limit.
Let us now discuss the theorems on limits. To obtain the limits of more complicated functions, we shall use the following theorems, which we shall state symbolically without proof. So the first theorem is that your limit of c, or the limit of a constant as x approaches a, is equal to the constant itself. So example of this one is that the limit of 5 as x approaches 3 is always equal to 5 or equal to that constant. Next is the limit of 3 as x approaches 2 is always equal to the constant 3, because we have nothing to substitute our values of 3 or 2 or any values that would be equal to or greater than 3 or 2. The next theorem will be the limit of x as x approaches a, which is equal to a. So if the value is just limit of x, therefore any value that would be substituted to x will be equal to the limit itself. Because take note that this is a defined limit. So example, so we have the limit of x as x approaches 5. So take note that this is your a, so therefore we may say that the limit of x approaches 5 is 5. The limit of x as x approaches 3 is always equal to 3. Therefore, whatever value of your x or whatever limit that you would want to be in x, like x as the x approach 5, so whatever the value will be your a. Okay, the third theorem will be the limit of a constant multiplied by a function can be rewritten into as x approaches a can be written into constant. So pwede nating ilabas yung constant multiplied by the limit of f of x. Example is your f of x is equal to 5x squared plus 5. So getting the limit of this one, so we'll have the limit of 5x squared plus 5 as x approaches 2, let's say 2, can be rewritten into, so factoring 5, so limit of 5x squared, so factoring out our 5, multiplied by x squared plus 1 as x approaches 2, so therefore it can be rewritten into 5, so ito limit of x squared plus 1, which is your f of x as x approaches 2. So by further evaluating this limit, so we'll have a value equal to 5 multiplied by 2 squared plus 1. Take note, pag define yung limit, we can immediately substitute the value of our x, which is equal to a. Okay, so we'll have 5 multiplied by 4 plus 1, so we'll have a value equal to 25. So next is that f of x, let's say the limit of let's say 5x cubed plus 25 x plus 10 as x approaches 1. Okay, so we can rewrite it into 5 multiplied by x cubed plus 5x plus 2. So this will be our f of x and this will be our c. So the limit of x approaches 1. Okay? So therefore, in other words, you can rewrite it into 5 multiplied by the limit of our x cubed plus 5x plus 2. So for further evaluation of this limit, so 5 multiplied by 1 cube plus 5 multiplied by 1 plus 2. So we'll have a value equal to 5 multiplied by 8. So we have 40. So the fourth theorem involving limit will be our limit of f of x plus g of x as x approaches a can be rewritten into the limit of f of x as x approaches a plus the limit of g of x as x approaches a. So example of this one is, if we have an equation, let's say we have the limit of 2x plus 1 divided by x plus 1 as x approaches 1. So we may write it into, so we can write into, let's say f of x1 will be equal to, okay, so I will manipulate the equation into 2x plus 1 divided by x plus 1. Okay, so we can write it into x plus x divided by x plus 1 plus 1, right? So how did it write it from x plus 1 divided by x plus 1? Ito kasi pwede mo manipulate into x plus 1 divided by x plus 1. Okay, so this, since these are like terms, I can maybe say that we have x divided by x plus 1, which is plus x plus 1 divided by x plus 1 is equal to 1. Okay, and this will be x. So let's say this will be my, let's say f of x, and this will be my g of x. So therefore, we can write it into the limit of x divided by x plus 1 as x approaches 1 plus the limit of 1 as x approaches 1. Okay, so therefore we'll have a value of 1 divided by 1 plus 1 plus 1. So we'll have a value of 1 half plus 1 or equal to 1.5. Okay, that is our example 1. So example 2 is that so we have two functions that can be seen in our limit. So let's say the limit of f of x plus g of x, wherein our f of x is equal to x squared plus 5 and our g of x is equal to x plus x cubed. Okay, so let's say as x approaches, okay, so therefore we may say that we have the limit of f of x squared plus 5 as x approaches to plus our limit of g of x, okay, which is equal to x plus x cubed as x approaches to, so we will have a value of 4 plus 5. plus 2 plus 8. So we'll have a value of 9 plus 10, or we have 19. That is the other use of our fourth theorem. For theorem number 5, we have the limit of f of x multiplied by g of x can be equal to the limit of f of x. So okay, as x approaches a, so limit of x as x approaches a multiplied by the limit of g of x as x approaches a. Okay, one example of this one is we would want to solve for, let's say, the limit of x squared minus 9 as x approaches let's say 2. Okay, so we would want to factor out into let's say I want to factor this function into to my f of x, to my g of x. So we can rewrite it into the limit of x plus 3 multiplied by x minus 3 as x approaches 2. So therefore it can be related into limit of x plus 3 as x approaches 2 multiplied by the limit of x minus 3 as x approaches 2. Okay, so therefore for further simplification of this, I will have a value of 5 multiplied by 1 multiplied by negative 1, so we'll have a value of negative 5. Wala pa, pag ito yung ginawa mong pag-direct synapsheet mo, since defined function yan, it will have the same answer. I just want to show you the use of that rule. Okay, for our sixth rule, so we have the limit of f of x divided by g of x as x approaches a, which is can be rewritten into the limit of f of x as x approaches a divided by the limit of g of x as x approaches a. So an example for this one is, let's say we have a function equal to the limit of let's say x cubed plus 3x squared plus 2x divided by x squared plus 2x plus 1, so as x approaches 1. Okay, so we may say that our f of x is this function, and our g of x is our second function. So therefore we may write it into, or we may evaluate it using this rule. So therefore we'll have a value equal to the limit of x cubed plus 3x squared plus 2x divided by as x approaches 1 divided by our x squared plus 2x plus 1 as x approaches 1. Okay, so therefore for further evaluation of this mathematical equation, so we'll have a value equal to 1 cube plus 3 multiplied by 1 squared plus 2 multiplied by 1 divided by 1 squared plus 2 multiplied by 1 plus 1. So therefore we will have a value equal to 1 plus 3 plus 2 divided by 1 plus 2 plus 1. So we will have a value equal to 6 divided by 4. Okay, so that will be the answer. So next example is the limit of, let's say, x cubed minus 1 divided by x squared plus 1 as x approaches 2. Okay, so if you want to re-evaluate it, if you want to have another solutions, or the best solution is that you can immediately solve the problem because it is defined. So therefore we'll have a value equal to the limit of x approaches to the limit of x cubed minus 1 as x approaches 2 divided by the limit of x squared plus 1 as x approaches 2. So we'll have a value equal to 2 cubed minus 1 divided by 2 squared plus 1. So we'll have 7 over 5. Rule. So we have our roots rule. So we have the limit of the nth root of f of x as x approaches a can be rewritten to the nth root of the limit of f of x as x approaches a. So the things to remember when dealing with this nth root is that your n is positive integer, and if n is equal to an even integer, f of x, which is equal to L, must be greater than or equal to 0. Therefore, if L is greater than or equal to, is less than or equal to 0 at even integer of n, we will produce an imaginary number. Example, so we have the limit of the square root of x squared plus 1 as x approaches 1. So take note that we may write it into the square root of the limit of x squared plus 1 as x approaches 1. So we have a value equal to the limit of x squared plus 1 is x squared plus 1 as x is equal to 1. So we will have a value equal to square root of 2. Example 2 is we have the limit of square root of 2x plus 5 as x approaches 2, wherein it can be rewritten into square root of the limit of 2x plus 5 as x approaches 2. So we'll have a value of 2 multiplied by 2 plus 5 is 9, or we have our 3. Okay, from square root of 9. So that is our 7th rule. For our 8th rule, we have the limit of f of x raised to n. So we have as x approaches a. So we have the limit of f of x as x approaches a. So close and open parenthesis is to n. Okay. So example is if we have the limit of x squared plus 2x plus 1 raised to as x approaches 1. So we can write it into the limit of, pwede natin ipasok yung limit, x squared plus 2x plus 1 as x approaches 1 raised to 2. So therefore, it can be equal to the limit of 1 squared plus 2 multiplied by 1 plus 1 squared. So we have 1 plus 2, 3 plus 1, we have 4. So the limit is equal to 4 squared. So it can be rewritten into 16. So next, equals like so next is example 2. Let's have our example 2. We have the limit of, let's say, x or square root of x plus 1 as x approaches 2. So take note that this is like our theorem number 7. So they are interrelated since you can transform our root into exponential function. Okay, so I may rewrite it into the limit of x plus 1 raised to 1 half, or it is relatable into the limit of x plus 1 raised to 1 half as x approaches 2. As x approaches 2, so we will have a value equal to 3 raised to 1 half, or square root of